Okay, so now I wasn't able to show that clip. It was just the lighting wasn't right. I was just getting a lot of reflection. So I'll show you tomorrow my Witch of Agassiz clip. All right, number 69 in your textbook gives you an example of the Witch of Agassiz, and it asks you to find the tangent at the point 2, 1. So it's not done any differently than any other curve. It just has an interesting background and name. So 8 over x squared plus 4. So you find the derivative. You're going to use the quotient rule, throw in the 2, and then use y equals mx plus b to complete the equation of the tangent of this curve at this point. And then I'll probably assign one other like that. All right. Let's look at, that's sort of a side note. Let's look at our topic for today. It is the chain rule. And the chain rule is called the inside-outside rule as well. I probably will forget to call it that because I was raised on the chain rule, but it does give a little more meaning to what it's about. So I'll show you both names. And it's used when you have a composite function, such as, say this function is, say there's a g function, we usually start with f, an f function, and inside of it is a g function. So that's when you use the chain rule to find the derivative. So we're asked to find the derivative of h. Now, it turns out that shows up a lot more than you think. So, for example, if you have y equals sine of 3x. So you know how to find the derivative of y equals sine of x. But now we have a function inside of the sine function, and that's 3 times x. So you may think that the derivative is cosine of 3x, but it is not. So when you have a function embedded in a function, that's called a composition, where we have composed functions, you find the derivative like this. And the proof for this is very easy to follow, and I'm not going to go through it. It's very similar to what we've seen with the quotient and product rules. So please read that if you are interested in seeing where it came from. All right. So the rule looks like this. When you're finding the derivative of a composed function, you take the derivative of the outside function, which is f, so that's where I say f prime, evaluate it at the inside function, and then multiply by the derivative of the inside function. So again, this tells me to take the derivative of the outside function and evaluate it at the inside function. And finally, multiply it times the derivative of the outside function. I'm sorry, derivative of the inside function. Now, this is a lot more complex to explain in the theory than it is to actually do one. So allow me to do that. And it's y equals, say, sine of 3x, the one I introduced a second ago. And what happens, say, we're going to follow this. It says take the derivative of the outside function. When I say outside function, I'm talking about the sine function. So it's sort of like I ignore this. and I just pretend that it's sine of something. I'll even cover it up with my finger, and I'll say, what's the derivative of the sine of something? Well, the derivative of the sine of something is the cosine of something. So in that step we did the derivative of the outside, we took care of this, and we took care of this. That's the 3x. So it was unchanged. So we're not done. And then times the derivative of the inside function. What's the derivative of 3x? The derivative is 3. So the correct answer, I'll put the 3 in front, is 3 cosine 3x. So let me do another one. Suppose we have y equals 3x plus 1 to the 7th. And this is the function 3x plus 1 is inside of an expression raised to the 7th. So we start out again. The derivative of this one is the derivative of the outside function. So we have something raised to the 7th. So the derivative of anything raised to the 7th, the 7 runs down in front, becomes coefficient, times that something, you can even leave it blank for a second, raised to the 6th. So now we evaluate that at the inside function. So it appears back in the problem, but we're not done, times the derivative of that inside function, which is 3. So these can combine to give us 21 and 3x plus 1 to the 6th. So why do we call it the chain rule? Well, it's a chain rule. I can see why it would be called inside-outside rule, but let's see why they call it the chain rule. And I guess the best way is we can have h of x equal f of g of x. That's how we start it. But what if g is in terms of some other function? Suppose we have g of something embedded in the inside function is another function, like s of t. So here we have a function embedded in a function embedded in a function. So it can actually go on as long as it wants to. So you can have as many in a chain, a long chain of these functions with inside functions. And the chain rule will get you through it every time. So I'll show you one where you use the chain rule more than once in just a minute. I wanted to show you Leibniz's, this is the more common expression for the chain rule, and that is, say you have y equals f of u, and you have, remember we have a function inside a function, so let me tell you what u is. U equals g of x. So that's not as complex as it looks. It could look just like that. So the outside function is sine, but the inside function is 3x. So in order to find the derivative, we can say dy dx. I want the derivative of the function y with the respect to x. So that's embedded inside. So dy dx equals, first of all, the outside function, dy with respect to the variable u, times du dx, the derivative of the function u with respect to x. And these can be thought of as small algebraic quantities. And so this could cancel this, and you would be at dy dx. So it should algebraically look sound. But what if we have embedded in this function, instead of x, we have something else, like t. And then t equals, I don't know, r of x. Then we add another chain to the link, because here we would have we would have dy dx equals dy du times du dt times dt dx. And you can see, if you were thinking about these as algebraic quantities, they would cross out and give us dy dx. But the rule tells me that I will find the derivative of this times the derivative of the inner times the derivative of the inner. So that's just another notation that's often seen, and it's all done exactly the same way. So let me show you another one. Maybe the hardest part is knowing when to use it. So let me show you once, and we'll discuss whether we use it or not. Y equals 3x plus 1. That is a function, plain and simple. There's no embedded function. It is not a candidate for the chain rule. How about y equals x to the 7th? Nope. All right, what about y equals 3x plus 1 to the 7th? We already did that one. But you can see the outer function is something raised to the 7th, and inside it's 3x plus 1. How about a situation where you have sine of 5x minus 2? It is a candidate. Outside function, inside function. What about the square root of 3x minus 2? It's a candidate. Outside function, inside function. So if you can find a function within a function, you can do the chain rule. So let me show you one last example, and that is y equals 1 plus cosine 2x raised to the 2. So here we have something squared, and inside of that we have 1 plus cosine of 2x, and inside of that we have 2x. So we have a function embedded in a function embedded in a function. So we're going to have to use the chain rule 3 times. So we're going to take the outside, the most outside function, so we ignore pretty much what's in here. And the 2 will run down in front and reduce to a 1, usually unwritten. And I'll go ahead and write what was in here. Doesn't affect this point. It doesn't affect this part. So now we want the derivative of that. And so the derivative of that is a negative sine of something. And that time, the part inside is 2x. It's not changed. And now we finish, because this is also a function, by multiplying times the derivative of the inside, and that's 2. So pulling that all together and cleaning it up a little bit, we get 4 and a negative out in front, sine of 2x times 1 plus cosine of 2x. And you're willing to multiply that out if you think that would help, but I think that's as good as it's going to get. All right, so we will try the chain rule. It will become so automatic that you won't think about it in this slow, halting way. But for now, this will get us started on our work tomorrow. Till then, adieu.